टिश्यू पेपर Okay, let's start. Board की quality बहुत खराब है. Board की quality. Well, let's get ready to start anyway.
Could we have some more input in theoretical accuracy and statistical accuracy in your lecture? Some more inputs. I want some more inputs regarding statistical accuracy.
So what do you want though?
Actually, why I understood is that statistical having a reference model.
Yeah.
Statistical reference.
That's correct.
Yeah, and in synthetical accuracy, you do not have any reference model or something like that.
Syntactical is the first thing that you do anyway. Make sure that the data that you're going to model, make sure that you've got your age is a number. Yeah. Make sure that your gender is male or female. Yeah. So that's just almost like an organizational thing.
No, can I add some attribute there in case of the statistical accuracy? Some enhanced attribute, not enhanced data.
So you can add some attributes, but how are you going to say whether that's useful or not? You've got to use some other kind of thing to do. Yeah, but it's possible, definitely.
Like we can add some aggregated attributes in that data, like where.
I wouldn't call it aggregated, but you can add a new attribute. So you could have something for fraud and say, I'm going to add in shoe size.
Right.
And you can do that. And it's not in the original data, but you say, oh, I know most people have got a size 8 feet, and I'll just do something like that. And then you might find, oh, actually, but I also know that the male feet are bigger than female, so you can do that. So you can do that and find out how it works, yeah. So you can definitely add different attributes and then use some extraneous knowledge to help. Okay, should we kick off? Okay, so I'm going to talk to you about trustworthy and private data sharing now. So this is work with, I mentioned PrivBase earlier. So that PrivBase was written by Graham Cormod, and in fact I'll wait because not enough people here. We're just waiting for your friend who was sat there behind you, yeah?
So please come.
Okay, we'll start then. Okay, let me tell you, so this work is joint with Graham Cormod, who did the PrivBase algorithm, done lots of other stuff as well. He's at the University of Warwick, but also at Meta, so half his time is at Meta. Who's a PhD student of mine a while ago and now works at the Alan Turing Institute, and Harsh Kashyap, who some of you know. Harsh was here and completed his PhD under Somanath as well, so it's great to be here presenting work he's done. I won't get through all of this, I'll get through as much as I can. So data sharing is really important in financial systems, and I know a couple of you are working in the area, but sometimes we need to work out something called KYC. Anyone know what KYC is? Very good. Know your customer. So we want to make sure that we're doing the working with the right person. So sometimes the name is fuzzy. So if I show you this name, Ilka Atmarka, actually he has two first names, yeah? And one, so they're both given names, but it's not like I have a middle name, yeah? So sometimes is called Ilka as one word. Atmarka is definitely the surname, the family name. And other times it's Ilka, etc. So you need sometimes fuzzy name matching. Sometimes anti-money laundering is something that we think is that is increasingly important in finance. And the problem with money laundering is money will go between banks, and banks will not share information about it. So if I am, let's say, some SBI is a bank, right? Yes. Sorry.
Yes.
Yeah. Yeah. So if I'm in that bank and there's some transaction and it goes to HSBC, a different bank, all you know is that it went to a customer account. Yeah. You'll know the account number that it went to. Yeah. But what happened to the money after that is invisible because it's in a different network. Yeah. So anti-money laundering is where each party, a party being a bank, has a partial view of the transaction life cycle. Also, you need to share data because the regulator might insist on it. And finally, you might want to have stakeholders come together and share data to solve the credit risk problem. But there are problems with sharing data. So understanding the risk of information disclosure, so disclosing your data or your models. Accuracy and timeliness, how do we do it fast? Yeah. How do we trust across different organizations? What about the scale? HSBC is a massive bank, for example. Sometimes there's law and regulation that prevents it, most notably GDPR stops you doing that. And there's a governance. How do you manage the transfer of data? So sometimes these are some of the challenges that we've got. So data is insufficient or obsolete, so it's old. Sometimes it's skewed. So this is the particular thing I was talking to you about yesterday. If you've got with fraud, it's a really small number of transactions. So how do you identify those in a big data set? Well, what's going on? There's a lot of development in silos. So there may be some, even with all those figures that you've got, there might be some extraneous circumstances. Moving data it can be difficult for security and privacy, and data sharing pacts and guidelines restrict data collection. So this is an important thing. I showed you this slide yesterday, and I want us to remember some of these pets.
Privacy enhancing technology.
Exactly, privacy enhancing technologies. Do you all know at least two pets? Write down at least two privacy enhancing technologies right now. I said write them down. One of them you should know because we just spent an hour on it, but yeah. Two of them you should know, we spent an hour on two of them. Let's see how well we do on the list. All right. Okay, start shouting some out. Differential privacy, I'll give you that because you said it first. What else?
Academic learning.
Good.
Adding noise.
Adding noise. Okay, that's differential privacy. Yeah. Anyone? Anything else? What did Somanath teach you? Homomorphic encryption. Aggregation. Good.
Anonymization.
Very good.
Data minimization.
Very good. Secure multi-party computation.
Multi-threaded learning.
Yeah, we said that. Trusted execution environments, said T's. Synthetic data, we've just spent an hour on. Yeah. Zero knowledge proofs, I mentioned yesterday as well. I think you've got quite a few altogether, okay. So, I'm not going to go through this because I don't have time, because I want to go through the thing that I... But basically, there's a large number of pets, and we've seen challenges with the Netflix data set, for example, right? So the Netflix data set was famous because what happened, Netflix started a competition, released a load of data, and then what happened was, in that Netflix data, you had records of what people were watching. Now they changed, it was all anonymized or pseudonymized, but the problem was you could correlate data that was given there with public data, and that is basically IMDb data. So you could see that somebody had watched film A in both, there was a record, if you just had a look at each user, in IMDb that people wrote who they were, yeah, and they would have matches, even if you changed it a little, and then you could find out, because there was no differential privacy, which is plausible deniability, yeah, there was a film that maybe was a little bit less socially acceptable, let's say, yeah? So if there was a film and you go, well, it's not in IMDb because they're not going to put it on there and make it public, but it is in the Netflix data. So as I mentioned, the established techniques, we've seen these. Differential privacy, essentially, this is a nice diagram to show you what differential privacy is. Two things that look the same, but they've got a small difference, okay? You'll have all these notes, actually. Secure multi-party computation. One thing I want to say is, and I don't know if it came across in Somanath's talk, but this is something, because I'm going to talk about homomorphic encryption now. This is the way you should think about homomorphic encryption, yeah? Is that in a standard model, yeah, what happens is we take some data, so if it doesn't have a padlock, it's unencrypted, okay? You take some data, you put encryption on it, you send it to the cloud decrypts the data, it then has this data unencrypted here, it does some operations on it, it gets this new version of the data, yeah? It then encrypts it again, you receive it encrypted, and then you decrypt it. And that protects here in the middle, that transmission layer, okay? But what it doesn't protect is against the cloud knowing something, because the cloud has learned this stuff. The cloud is a trusted party in this, yeah? You have to trust the cloud that they're not going to do anything bad with your data there. So, homomorphic encryption is take your data, encrypt it, it goes to the cloud encrypted, yeah? And the cloud then does some operations, sends it back to you encrypted, and then only you can decrypt it. So it's not the easiest concept to get around, but someone told me a really good example of a way to think about it. Think that you take some data and you put it into a box, yeah? So the data is locked, it's in a box, yeah? You send it to the cloud, and what happens is the cloud provider, the service provider in the cloud, has got some special techniques that what it can do is it can push and poke the data while it's still in the box, and it is manipulating it for you. And then when it's finished its manipulations, you get the data back. Everything's been changed in the box, but you can't, they never saw it. They've got these special called homomorphic techniques that they can do. Yeah, so think about it, it's in a box, but you can do some little thing and it'll push two numbers together, it will add them up, yeah? And then they're added up, it comes back and you have it added up. And that's what's really important, because the secret source, the thing that they're going to be charging you for is, hey, I can do this in the encrypted domain, okay? So that's homomorphic encryption, and we're going to talk about that today. There is an example in practice with Duality, a company that's led by Shafi Goldwasser, Turing Award winner, very famous person, and Kurt Roloff, who I know very well. They've got this company called Duality, and working with Oracle, database company, they've created a homomorphic encryption solution that was run in the US as a pilot. So what do we want to do in my research problem? Well, what we want to do, yeah, is, what we want to do is secure and private fuzzy name matching, okay? So what we want to do is, I don't think I've got an example of it here, just one sec. Okay, in fact, I'm going to go up, I've got time. I have got some time actually to show you this. Okay, let me go through the Duality solution first, because this is not fuzzy name matching, but this is standard name matching, okay? So what happens is you have a bank A, yeah? So what you want to do is financial institution A has got a query. It wants to ask something of a database. Basically what it wants is a match, right? So it's going to encrypt with a public key, right? So the thing is with this public key, only it has the private key, okay? And it says, do you have a client with this set of identifying information? So we're going to do a KYC across banks here, okay? So, and you can automate it or not. You send it to Duality and Oracle, who are coordinated. Now the thing is, this would be, if it wasn't encrypted, this would be a trusted third party, right? But they're not, because you have sent them something with your public key. It's encrypted with your public key, yeah? And therefore, they've got something that's encrypted, but only you have got the private key, right? So there's only you that can decrypt that, yeah? So what they do is, Oracle know which institution the query is to be sent to. Sorry, that's wrong. Sorry, the public key that you use is the public key of one of these, yeah? Because they've got a private. Is that correct? No. Sorry, it's your public key. The Oracle, you tell them which institution it's going to go to, but they don't tell you, don't tell them what the query is. That's in the encrypted domain, okay? So what you do is you send it to all of the participants, yeah? But the knowledge that you've got at Duality is that Duality knows two things. What is the original, sorry, they know one thing. What is the original A? That is unencrypted, so because they're going to charge you, right? So financial organization A sends a query to Oracle. Oracle receives it. It's encrypted. It can't decrypt it, but it knows it came from that particular financial institution. It's then going to send that to all of the other institutions, yeah? And what it's doing is it's blinding, because it knows where it came from. It is blinding from B, C, and D. They don't know which organization sent it. It could have been A, it could have been C or D. B doesn't know if it's any of those. C doesn't know if it was A, B, or D, etc. Okay, they all know who's in the community. They know A, B, C, D, but they don't know which one it came from. Okay, so it goes to all three. They then look at their database, yeah, and the encrypted results are sent back to Duality, yeah. So this is still. So the thing is, the encrypted query runs here. Yeah, so they've never seen it, but they run it on their own database, okay? So when they run it on their own database, yeah, they're doing a fuzzy name match. They're doing what's called not fuzzy, sorry. They're doing a name match. It's called a private set intersection, yeah? They're saying basically, is there a match between the person that I've got from whichever bank and my data? And that answer, yeah. So what will happen is you've got some encrypted text, yeah. Some encrypted text, you don't know where it's from, doesn't matter because you're going to send it back to Oracle. It came from Oracle as far as you're concerned. As somebody who's going to answer the answer, you get some encrypted text, which is a name, yeah, and it's encrypted with, in this case, it's A's public key, yeah. You've got an encrypted name, you do a match in the encrypted domain, you check it with all of your database. Yeah, check it in all of your across all of your database, and you will then get a single answer, yeah, which is encrypted with A's public key, which is a yes or no, yeah. So at this stage, every one of these is sending back a yes or no. Comes back to there, they aggregate that, so the yes or no is zeros or ones, yeah. They aggregate it, so now when the answer comes back to here, Duality will know who sent a response, but will not know what the value of the response is, okay? They will just know that they sent a response. They aggregate it and then send that back. And now this, using the private key, can just turn back, and it will basically get a 0 or 1. If these were all zeros, yeah, it would get a 0 back. If any of these were 1, you've got two choices. You can add them up so that it would say 3, it's in 3, or depending on the function that they use at Duality, they could cap it at 0 or 1, yeah, using ReLU or something like that, yeah. So that's the Duality solution that works in practice. It's reasonably efficient, but it only works on real matches, because matching real names is quite easy. Matching fuzzy names is much more difficult, as Harsh will tell you. So what we're trying to do is we are looking to see two words, yeah? We're looking at W1, which is, the word is the name that you're matching on, okay? So let's have a W2. We're going to do lots of these matches. So it might be, did I spell your name right, Somanath? Is that correct?
Yeah.
Yeah, and you might check it against. Yeah, I've got these are the different words, right? But you might have in this set, this W2, now you'll notice I've misspelled here, right? So there's a word difference, yeah? Or you might have in this set, yeah? Now the question becomes, how close, yeah, are these two words, W1 and W2? So if this was W1 and this was W2, would you say they're close? If this was W1 and this was W2, would you say they're close? Yeah. If this was W1 and this was W2, would you say they're close? No. Who says, put your hand up, you say no? It's fine, just put your hand up.
Yes.
So I think these two are easy just to swap names around, because it's what we call one move away, yeah? I think it's probably as easy to get the, you're filling in a form. Have you never done that, where you fill in a form, it says first name, second name, you write it the wrong way around? I think these two are similar, but they're different. Actually, if you look at different, what we call distance metrics, they're very different, right? Imagine there is something called a Levenshtein distance. Yeah, and the Levenshtein distance effectively says the difference between two words is how many letters you need to add, yeah, replace, or delete, yeah? Yeah, and every time you add one, so the difference between this would be very small because it's one addition away. And the distance between this and this would be massive because there's loads of changes you need, you know, because there's no C in here, right? So I'm going to have to immediately change that C for something else to try and get to this. It's the minimum number of moves, yeah? But if you look at this, yeah, I'm going to have to do something like, I won't have to change any letters, but I'm going to have to move that to 1, that to 2, that's going to have to go to 3, all of them. Yeah, I think they're all going to have to move. Everyone moves, yeah? So it becomes lots away. But in names, we could define it just as one move, right? Because it's just swapping. You shouldn't really consider it the same as something really quite different. You know, imagine I just randomly scrambled that. Then that's definitely going to be something different, right? So what we're looking at is we're trying to find something that defines where these words are close. So do they logically match? So what we do is we do something called locality sensitive hashing. Has anyone heard of locality sensitive hashing before? Okay, it's quite a famous technique, but you won't have heard of it too much necessarily, but it's used a lot. Has anyone ever used Google reverse image lookup? You ever done a reverse image lookup? No? Okay, well, let me tell you, there are techniques now by which you can say, if I've got one picture and another, yeah, they're both files, if I hash them both, you know what a hash is, right? It takes it into a reduced space, and a hash takes a file such that if you hash a hash of any kind of file A, yeah, if that equals HA, yeah, then one thing that's important is you cannot get A from HA. It's got to have some randomization, right? That's what a hash is about, yeah? And then also a hash from of A plus epsilon, a little perturbation, yeah, tiny thing changes. If that equals HA epsilon, then what you need to do is HA is, you cannot derive from HA epsilon HA, but also is that it's a large difference, right? So just making a small change in the hash gives you a big distance. So this is really for integrity of stuff, right? Now, locality sensitive hashing is a really bad term because it's completely not a hash. What it does is, what you do is you take an LSH of a file A, and let's call that LA, yeah? Then what you can do is LSH of A plus, I'm going to call it O, which is some operations, right? So in an image, what I could do is rescale the image, make it bigger. Now that is, if it's a hash, it's going to make lots of difference, right? Yeah? If it's a, if I change a color thing to a black and white, that's loads of difference in the hash as well. But a locally sensitive hash of A, I can do a good number of operations, and it will give me LA of O equals LA. It doesn't change the hash. It is invariant to a number of operations, yeah? And that's why you can do, and I try and do this today in the lunch break, a reverse image lookup. So get an image, yeah? Any kind of celebrity or something like that, yeah? And then do a reverse image lookup. And it should give you not just the original image, because it's not a hash, but something that's like it. So one way you can do this is, and I did it before myself, there was a picture, I was looking at something called cyberstalking. This was like 12 years ago. And there was a picture of a guy, yeah, and he'd blurred his face out, yeah? And he'd got a gun with him, he was threatening someone, an MP as it were, yeah? And what I could do is the top bit of the picture was exactly the same elsewhere, which was unmarked, was in the clear, and Google managed to find the original, because what they said is they found lots of similarities. Think about like those biometrics. A biometric, yeah, takes some of the key information and the other information doesn't matter, yeah? So if you remove it or add something else, that information, there's still the DNA stays the same. And in fact, that's why it's called photo DNA from Microsoft, yeah? So that's what it is. That's a locality sensitive hash. So what we do is we take a name and we say, because look, what we're doing, what we want to do is have some hashes where it's the same even if you do some operations, yeah? So you're binning similar things together, yeah? So that's what we did in our process. We put similar points hashed to the same buckets, yeah? So general hacking, you get that, and it will go here. You move it a little and it goes somewhere wild up somewhere else. This point will go here. And what you do now, because these are close together, they go into the same bucket, and because these are close together, they don't go into the same, but they go to close buckets, okay? So this is what our process is. So you have an organization A, which is a querier, yeah? So the first organization wants to say, so let's say it's my organization, Somanath, and I want to say, Somanath, do you have this information in your thing? But instead of saying have it exactly, I want to catch if somebody's been cheating or there was a little mistake, like here, probably a typographical error, right? So I want to work out if that's like this. So what I do is I have a data lake in an anti-money laundering system. I have a customer name and a date of birth, okay? I hash those using this technique that says, okay, so I've got my A and I put it into a hash out of A. I take the signature of that and do some pre-processing, and then I put it into the homomorphic encryptor. So I encrypt it with my public key. So it's now in the encrypted domain, yeah? And what I do then is I say, right, this is organization B, yeah? Now what they have done, don't forget, I've sent this with my public key, yeah? So that public key, A's public key, is anyone can have it, okay? So in particular, B has got A's public key as well, right? So what B does is it's got all of this stuff here, yeah? All of this is plain text because B owns this data, right? It's got its own data, it's got the same locality sensitive hashing algorithm, yeah? So therefore, if B has got, if this is A and B, yeah, this, yeah, in fact I should call this W1, and this W2, W3, W4, yeah? What happens is, you start with, what B can do is, it knows the hashes of these, its own hash, because it's, that locality sensitive hashing is available to all parties, yeah? So what it does is it hashes these, yeah? It then gets a request that comes across in the encrypted domain, but it's okay because it encrypts all of these with A, yeah? It does a matching in the encrypted domain, yeah? So it's in the encrypted domain that it does a matching, and then it will send the results. A then decrypts the results, yeah? So A decrypts the results, and if it comes back as a 1, yeah, it knows that that name was in the database, and if it comes back as a 0, it knows that name is not in the database. Okay, so let's have a look how it works in practice. This, okay, good. Okay, so you start with the responder, B, right? So that's where we're going to start at the moment, right? So B has got a number, it's got a long list. So here's server B. It's a bank, yeah? And it's got a long list of names and dates of birth, yeah? So that's all its customers on its risk list, yeah? So what does it do first? Well, what it does is it encodes them and creates LSH hashes of them, okay? So it gets yeah, so it can do this. And the good thing is, this locally sensitive hashing, it can do it once. For any query that comes in, these don't change. These are not query dependent, okay? So it has a big list of capital D of these. Yeah? So it gets D of those, and the first thing it does, it says, well, actually, to work through all of those D in the encrypted domain is a bit of hard work. So what I'm going to do is I'm going to create clusters instead. I'm going to create centroids, because remember what I said here, similar things go into similar hashes. Yeah, that's an important thing about the LSH, right? So what I do is, instead of this long 1 by D, yeah, vector, I turn it into a root D by root D.
How do you make it? How did you make it? There are things coming from the same cluster.
Sorry? So how do I work out the LSH? Yeah.
Now, how do you calculate the LSH?
You just do a clustering technique.
Okay.
You just cluster the hashes.
Okay.
So you do a similarity clustering. So nearest neighbors clustering.
If I do has do it entirely different, right? It comes at random. Right?
Not a locally sensitive hashing.
That I'm asking, how do you do the locally sensitive? What is it?
So that there's a bit of secret sauce. Not secret. It is something called shingling. You take these 3 grams. What you do?
Yeah, we do consider the things. The playgrounds, right?
Sorry.
You took the playgrounds.
Yes. Yeah.
All right.
Yeah. But you do these, and it definitely works. That means you get a small variation.
Exactly.
But what the aim would be to do better words that you can get these to be similar for the hash as well.
But
So
every take the trigram and then hash it. Is it that you're doing?
Yes. Yeah. We get a set of strings of length k. Yeah. So we do this shingling, then we do a hashing. Yeah. And then you do a permutation.
If you don't mind, can I take an example? We need the trigram. Let's take an example. Taking an example, let's see.
I can't do that right now because I can't. It's too long to go through it. And I definitely can't do the 256 hash. But I can go through it, and it's in the paper from Hodge.
We did the trigrams, and then, of course, we did it in a different way.
Yeah, so this LSH algorithm is really important. The better one you've got, the more it will get some of the similarities. So I think we use min hash is what we used. You know the min hash algorithm?
Yeah.
Yeah. So that's what we used. And it tended to work well. We did that empirically as well. Okay, so what you've got is root D clusters. Now, I've turned this into a set of clusters of root D by root D. Yeah. And they are clustered along rows here. Okay? And the way that you do it is, so each row is similar, yeah, in terms of hashes. And what happens is A sends in the encrypted domain with public key of A, it sends the name it wants you to check, yeah? What you then do is you calculate, and here again you've got different scores that you can use, but we do cosine similarity. So you can do cosine similarity of the centroids, yeah? So remember, I've created this matrix, D by D matrix, and within there, Each of these has got a LSA in it for each of the names, yeah? And they're all similar, so each row is similar. So what I can do is I can work out the centroid of this row, yeah? So what's the centermost of these? I don't need to do it in the encrypted domain. I can do that in the plain domain because I know all of this, right? So I work out the centroids. So you've got the centroids here. So this is a vector. And what it is each of these is close, the centroid is close to each of this root D element, yeah? And what I do now is in the encrypted domain, yeah? In the encrypted domain, I'm going to work out the distance between these and the single element that came across, which is EPKAN, yeah? So I can do that in the encrypted domain because all I'm doing is a distance, yeah? So I work out the distance between the name and each of my centroids, and I send it back. And what happens is I send back to A, then I really need a port rubber. Let's see if this works. Yeah. So at this stage, yeah, what I'm sending back is in the encrypted domain, yeah, I am sending back effectively a vector. So because it's encrypted, B can't see it, but what's in here really is the distances between the encrypted number, yeah, and the other. But what I do is I do a little function that basically says I'm going to send back lots of zeros, yeah, apart from a 1, because I can do a ReLU kind of operation here, right? So from the cosine similarity, I can make sure then, even in the encrypted domain, I don't know whether I'm pushing to 0 or 1, but I know I'm pushing to one way or the other. And what happens is A can now decrypt this, because it was locked with A's padlock, yeah? It can decrypt it, and it can find if there is any similarity where it is, yeah? If it all comes back and it's all close to 0, it knows there was no similar match in B's data set. If one of them comes back with a 1, yeah, or close to a 1, it knows that that is close to the name that it sent, yeah? So what it then does is it says, okay, I know that this is the one that's close or the closest, yeah? And it sends back to B a vector, which we're going to do a multiplication of now. And what we do is we send back an encrypted vector, which is 1 by root D. And basically everything in that vector is a 0 apart from any potential matches, okay? So, and then what you do is if you take the vector that comes in, so the vector that goes back to A now, yeah, well, I send to B this vector, yeah, and it is very close to 0 and 1 because all that A has done is encrypted 0s and 1s. And when you encrypt something, yeah, this is using CKKS. You talked about CKKS yesterday. This has got some error noise in it. It's nearly 0. It's like 10 to the minus 6. And this is 1 minus 10 to plus or minus 10 to the 6. Minus 6, yeah. I can do that, and what it will do is it will identify in here, yeah, because loads of zeros, I'm going to get 0 for that. Whatever that was there is going to be 0. Whatever that was is 0. Yeah. Sorry, that one. That one's going to be 0. And actually, this one is going to be a number. Oops, this is going to be a number that is 1 times whatever it was. So it's close to its original number. And what you're doing by doing that is you are actually pulling out that row. and making everything else 0. So now everything else is 0 apart from the cluster that was close to the original query. Yeah? Now what I can do is I can sum each column here, right? Now then, that's going to be close to 0, right? This multiplying thing is going to be close to 0, close to 0, close to 0, close to the original similarity, close to 0, etc. So if I add up in the encrypted domain all of these, I'm going to get something that is close to the original similarities, yeah? And now I can send this vector back to A, and it can work out what's the closest similarity. So maybe if I got a couple of minutes, I'll show you with a kind of example. So let's imagine that the LSH, what I'm going to do is I'm going to get these cosine similarities, actually. Yeah? Imagine the cosine similarities are like I'm going to just do 16 for you, okay? So imagine that these are like 0.12. Right, imagine these are the cosine similarities that I've got between my my original data set and the encrypted data. So all of this, because these are the cosine similarities, they're in the encrypted domain, okay? When they were the local sensitive hashings, that's fine, but these are in the encrypted domain, yeah? So what we're doing now is we get the centroid, yeah? So something in the centroid of this is probably about 0.18, yeah? The centroid of this is something like 0.15. Centroid of this is something like 0.9, and the centroid of this is something like 0.4. Do you see what I mean? Yeah? So these are all close. So what I'm doing is on the stage where I send these to A says this one's close. So it sends me back a vector of 0, 0, 1, 0. Yeah? Now this one in the encrypted is exact, yeah? But when I take it into this, it was exactly 1, but when I encrypted it, it had a small error. Agreed? These all had small errors. They're not integers anymore because of the way CKKS works. I then multiply it by this. Now I'm going to get 0.1 times something really tiny. Yeah? So hopefully you all agree that's going to be 0, pretty much, yeah? So that becomes 0, that becomes 0, that becomes 0, that becomes 0. And all of them become 0, apart from this, which is approximately 0.87, approximately, yeah? I.e. they're all approximately biggish numbers. I add them up, yeah? And I get some number that's approximately, again, 0.87, 0.92. Right, now so long as the noise is not too much, and typically you're talking about 10 to the 6, 10 to the 9, 10 to the 12, sorry, not 10 to the 6. You're talking about 10 to the 9 or 10 to the 12, yeah? If I send this back now to A, encrypted, A can work out that 0.96 is the biggest, which basically tells him that he knows it was the fourth because it came back 4. It's in the 4th row, yeah? Fourth column and 3rd row. So first of all, A now knows that it's something that's close, and B, if A wants to send back, can say, send me whatever is in your 4th column and 3rd row, yeah? So that's the algorithm. We do this clustering rather than manually, because if you don't use the clustering, it can take a lot of computation. We've done something, but what matters is with your locality sensitive hashing, you've got to be careful, just as Somanath said, about how you design that LSH, because there are parameters that you can use. There are parameters that you can use in how you do that encoding. Yeah, so yeah, so the LSH matters, and what you're better with typically is a larger LSH. The number of clusters is important, because the number of clusters, when I did this root D by root D, you've got to be careful about forcing things in that are a long way away. You're never going to get these perfect clusters, right? So what you might have is some cluster that's, you know, if you did your clusters, it's not going to be root D by root D, but what it's going to be is some clusters will be like that, have that many elements, and some will have less, and some will have more. And maybe this is root D here. Yeah, so you're going to have more columns than root D. Yeah, and these are just going to be packed with zeros. Yeah. So what matters is how many clusters have you got in your thing, so how fine are you going, how many columns do you split it in, and then you get different timings, yeah? But what also affects is, because of the LSH, how you're doing that binning at the end, yeah? How many bins are you going to have, 50 or 100 or 200, changes the size of your encryption. So, of course, the encrypted message is much bigger, yeah? Then we've got the centroids and the signage values, but the results that we've got so far are very positive, yeah? So this is correctly identifying names, so we can see the impact. So here's the accuracy, precision, recall, and F1 score of the work, depending on what you do for your cosine similarity threshold, so where you set that. Yeah, and we've run all these tests on the NCBRD data set. So yeah, the results look pretty good. I think we've just submitted that to one of the large conferences. But that is the work that Harsh has been probably leading on, led with me for some direction, but Harsh has been doing all the programming on it, and all of the and some of the maths supported by UR, and guided by myself and Graham. Okay, any questions on that?
What will be the range of epsilon? What will be the range of epsilon?
In where? Which epsilon are you talking about?
Hashing. In hashing.
I'm trying to see which epsilon you mean, sorry.
So that whole, to go back to that slide.
This slide?
Previous here, the goal.
Where's the goal?
Find that value.
The goal finding. Last second line.
Yeah, I can see the goal. I'm trying to see an epsilon.
So it's not epsilon.
There's no epsilon.
Epsilon.
There's no epsilon there. This says, this is, AI is in a set between 1 to k, such that there exists a j in 1 to L, where AI and bj equals 1. So it's basically just saying, this just says the fuzzy match is close to 1. You know, I just drew all these numbers here. It's just which of these is close to 1. That means it's a match. Yeah, so this phi is a function. Yeah, sorry, psi is a function.
I understand.
Yeah, there's no epsilon in there. It's just you've got a function that's defining. Remember, so effectively what that's saying is your function. An example of a function could be a Levenshtein function. Yeah, but the function is defined such that this string is close enough to this string. It's a fuzzy match that says that is a match, so that equals 1, this equals 0, that equals 1, and if I put Narendra's name, it'll be a 0. Yeah, that's all that's saying. Any other questions? Okay, well, we've got a break. I will see you at 2:30. Thank you.